we've seen now that we can apply linear transformations in different coordinate systems. The transformations that we've been performing before have all been with respect to the standard basis. So in the last video, I said, look, in standard coordinates, if you have some vector x in your domain and you apply some transformation, then let's say that A is the transformation matrix with respect to the standard domain, or with respect to the standard basis, then you're just going to have this mapping. You take x, you multiply it by A, you're going to get the transformation of x. Now, in the last video and a couple of videos before that, or actually the one right before that, we said, well, look, you can do the same mapping, but just in an alternate coordinate system. You could do it with respect to some coordinate system, or in some coordinate system with respect to some basis b. And that should be the same thing. It should just be a different transformation matrix. And in the last video, we actually figured out what that different transformation matrix is. We had a change of basis. So let's say we had this basis right here. Let me actually copy and paste everything so that we understand what we did. So this was the example. Let me copy it. Let me paste it up here. Put all of our takeaways from the last video up here. Let me paste it right here. So in the last video, we said, okay, this is my basis right there. And then we said, let me copy and paste. That was my alternate basis. And then I have my change of basis matrix and its inverse. Those will be useful to deal with. So let me copy and paste that. Okay, copy. And then I'm going to paste it. Edit, paste. Maybe I'll just write it over there. Not maybe the best order. Maybe I should have written that first, but I think we get the idea. And then we want to write what our transformation matrix is with respect to the standard basis. And I wrote that right over here. This was all from the last problem, if you're wondering where I got all this stuff. Let me copy and then paste that. Edit, paste. So I'll paste that. And then the whole point of the last video is we figured out what the transformation matrix is with respect to this basis. With respect to this basis right here. So D, which was the big takeaway from the last video, was equal to this right here. Let me copy and paste that. Copy and paste. And now we have all of our takeaways in one place. Edit, paste. And what I want to do in this video is to verify that D actually works. That I could start with some vector x that I can, let me write it up here. Let's take some example vector. So this transformation, its entire domain is R2. So let's start with some vector x. Let's say that x is equal to, I don't know, let's say it's equal to 1 minus 1. Now, we could just apply the transformation in the traditional way and get the transformation of x. So let's just do that. The transformation of x is just this matrix times x. And so what is that going to equal? Let me see. Maybe I can just do it right here in this corner to save space. So it's going to be this matrix times x. So this first term right here is going to be 3 times 1 plus minus 2 times minus 1. Or plus 2, right? Minus 2 times minus 1 is just 2. So it's going to be 3 plus 2. So it's going to be equal to 5. And then the second term right here is going to be 2 times 1 plus minus 2 times minus 1. Well, that's just positive 2. So it's going to be 2 plus 2. So that is 4. So that's just the transformation of x. Now, what is this vector x? What is this vector x represented in coordinates, or I guess we could say to this alternate basis coordinates? So what is that vector x represented in coordinates with respect to this basis right here? Well, you saw before, I wrote them out here. Maybe it'll be useful to do it right here. The coordinate, I'll copy this little. Actually, let me copy both of these. These will both be useful. Edit, copy. As you can see, if you want to go from x to the x in an alternate basis, or the alternate coordinate representations of x, you essentially multiply x times c inverse. But that's why I'm copying and pasting it. Let me copy, and then let me put it up here so that we can apply these. So then paste it right there. So if we want to go if we want to go from x to the b coordinates of x, I take my x and I multiply it times c inverse. C inverse is this thing right here. So if I take x and I multiply it times c inverse, and I multiply it times t inverse, I'll get this version of x. So let's do that. Maybe I could. So this times that. Let me just put the minus 1/3 out front. So it's going to be equal to minus 1/3 times. Let's see if we can do this one in our head as well. So it's going to be 1 times 1 plus minus 2 times minus 1, which is just positive 2. So it's going to be 1 plus 2. So it's going to be equal to 3. And then it's minus 2 times 1, which is minus 2, plus 1 times minus 1, which is just minus 1. So it's minus 2 minus 1. It's minus 3. So if we have minus 1/3 times this, the b coordinate representation of our vector x is going to be equal to minus 1 and then 1. Just like that, which is actually interesting for this example. It just kind of swapped the first entry and the second entry. Now, let's see what happens when we apply d to x. So if we apply d to x, right, d should be our transformation matrix if we're dealing in the b coordinates. So let's see what happens. So if we apply d to x, let me scroll over a little bit. Just so that we get a little bit more real estate. So if we apply d to x, what do we get? And so this is going to be the transformation, or this should be the transformation of x in b coordinates. So what is this going to be equal to? We have to multiply this times d. So it's going to be minus 1 times minus 1, which is 1, plus 0 times 1. So it's just minus 1 times minus 1, which is 1. And then we're going to get 0 times minus 1 plus 2 times 1. So 2 times 1 is just 2. 2 times 1 is just 2. Now, for everything to work together, and assuming I haven't made any careless mistakes, this vector right here should be the same as this vector if I change my basis. So if I go from the standard basis to the basis b, and when you go in that direction, you just multiply this guy times c inverse. And I'm just using this formula right here. If I'm in the standard basis, I multiply by c inverse, I'm going to get the b basis. So let's see what I get. So this guy, I'm going to multiply him times c inverse. Let me do it up here just to get some extra space. Let me do it right here. So I'm going to multiply the vector 5, 4. I'm going to multiply that by c inverse. So we're going to have minus 1/3 times 1 minus 2 minus 2, 1. Just like that. So this is going to be equal to, I'll just write the minus 1/3 out front. And we have 1 times 5, which is 5. Let me just write this right. 5 plus minus 2 times 4. So 5 minus 8. 5 minus 8. And then we have minus 2 times 5, which is minus 10. Minus 10. And then we have 1 plus 1 times 4. Minus 2 times 5, which is minus 10 plus 1 times 4, plus 4. So this is equal to minus 1/3 times minus 3. And this is what? This is minus 6. And if you multiply them minus 1/3 times it, all the negatives cancel out, and you get 1 and 2, which is exactly what we needed to get. When you take this guy and you change its basis to basis b, or you change its coordinate system to the coordinate system with respect to b, you multiply it by c inverse, you get that right there. So this literally is the b coordinate representation of the transformation of x. We just did it by multiplying it by c inverse, which is exactly what we got when we took the b coordinate version of x, and we applied that matrix that we found, that the transformation matrix with respect to the b coordinates. When you multiply it times this guy right here, we got the same answer. So it didn't matter whether we went this way around this little cycle or we went this way. We got the same answer. This isn't a proof, but it shows us that what we did in the last video at least works for this case. And I literally did pick a random x here, and you can verify it if you like for other things. Now, you should hopefully be reasonably convinced that we can do this, that you can change your basis and find a transformation matrix. We've shown how to do it. But the obvious